Oh, hello. I didn't see you there. My name's Aryaan Bhimani, and I am a 16-year-old TKS student at TKS Toronto. One of the things that I'm super interested in right now is something called quantum computing. And I kind of want to explain to you some of the things that I've learned about quantum computing so far. So stay tuned. Today, I'm here to talk about a focus that I'm currently super interested in called quantum computing. Now, quantum computing is based on a type of physics called quantum mechanics. And one of the super cool applications that I'm super interested in is quantum computing. Today, I actually want to talk to you about what quantum computing is and what computing actually is. So let's start off with the basics. Computation. What is computation? Computation is processing information. Now, you may ask, how would a normal computer process information? It's like a method of addition, subtraction, and finding the right result that you're looking for using gates such as AND or FOR and NOT, like many types of gates that computer scientists use to actually compute a certain result that they're looking for. Now, one of the words that I probably just used, or that we actually need a definition of again, is information. Information is literally just a state. So it's super important to understand these two pieces of information as a foundation for computation and quantum computing. So information can be in a state in normal computers. It's usually in a state of either ones or zeros, which is called a bit, and in quantum computers, it's something called a qubit. So now let's talk about the differences between a normal computer and a quantum computer now that we've understood the fundamentals. So a quantum computer is able to do calculations with a combination of zeros and ones at the same time using a qubit. So a qubit has a possibility denoted by alpha for a 1 and denoted by a beta for a 0. So this is just like how quantum computers or physicists are denoting zeros and ones, like the states of zeros and ones. And this is a probability in complex numbers that this will be a 1 and this will be a 0. This is something super interesting called superposition. But enough for actual quantum laws for now. Let's talk about one law in particular that I actually want to talk about in this video, called the Heisenberg Principle of Uncertainty. Now, the Heisenberg Principle of Uncertainty states that you can actually only calculate one property pretty accurately of a qubit. So a qubit can be many things. It can be an electron, a photon, something that basically follows the laws of quantum mechanics. And what happens is that due to this law, we can only actually measure, let's say, the momentum, or we can measure the position of a quantum particle, which is a qubit. So that means that we're not actually able to control what a qubit is actually showing. We cannot really control if it's going to be a 0 or a 1, which allows us to actually enable the multiverse theory of quantum mechanics. This is a theory that I actually wanted to present to you in this video today. So the multiverse understanding of quantum mechanics. Now, it's actually super interesting, and this has been interesting me for quite some time now, ever since I started my research into quantum mechanics. And I really want to share my insights or understanding with you so far. So to understand what this actually is, we have to start off with a graph. It's a pretty easy graph to follow for the initial stages, because all it's a graph of space and time. So those are the variables. The independent variable is the time, and the dependent variable is the space. So now, with the Heisenberg uncertainty principle, let's just consider a flashlight for now, because we know for a fact that flashlights have something called photons in them, which follow the law of quantum mechanics. So let's just use that for now. And basically, a Heisenberg principle of uncertainty happens because a photon or something following the quantum principles have both a particle measure and a wave measure. So we're only able to measure one of them at one time, and we're not able to measure both of them at the same time. So we can only be a certain amount of accuracy of either one of the properties. So let's start off with a pretty simple flashlight. So at a certain point in time, there's this flashlight, and there are waves coming out of the flashlight. Let's just use 3 because it'll get a lot more confusing the more you add. So let's just forget about quantum mechanics so far, or actually let's just forget about quantum computing and using bits and qubits and stuff. Let's just first think about this wave. So at the next point in time, what happens is there is actually a stage where all of these are uncertain. Now, because of this uncertainty, because of this law once again, let's say at this point in time, it could be in any of these 2 stages. Let's say this photon right here, this photon reaches this point in time, and then at this point in time, because of the law of uncertainty, it splits up again because we don't know where it could be going, because the position is very uncertain to us. So now we can go to the next point in time. So now at any point in time, the 2 photons could interfere because of another law of quantum physics, but let's not really dwell on that right now. Let's just continue thinking that it basically creates its own thing. So these photons are being calculated or computated in a sense because it is processed through time. And now at the end of, let's say, this experiment, if so this has to be a closed loop for this to actually occur. Now let's say if a person comes to this loop, opens up this loop, and looks at the first thing. What this will basically do is it'll collapse the entire thing, and this person's wave function will basically be changed because of measuring this quantum particle. Now, one of the things that the multiverse theory incorporates is the idea that once a quantum experiment occurs, one possibility will occur in your eyes, and the other possibility, let's say, which is this one, will occur in an alternate universe. So let's say your phase is changed due to looking at this qubit. There are many of you actually in different universes seeing the different values. Now let's say if this works for a computer, which is super insane. Let's say if this instead was a bit or many bits, and these bits kept changing its position and kept computing. So imagine these are actual computers where it could be a 0 or a 1, 0, 1, 0, 1, 0, 1, and so on. Every one of them would have literally a different combination, which could basically mean that you could compute so many things at one time. This can literally be a separate computer, and you're computing things in parallel, which could exponentially increase the amount that we're able to actually calculate. So now let's think about the potential difference between a quantum computer and a normal computer. So as we know, a computer can only use bits, which is 1s and 0s, right? But a quantum computer can use a combination with a probability, right? So this would be the probability of a 1 and a probability of a 0. Now, because of this, okay, so now let's compare this to this. So mathematically, this can only calculate 2 to the n times. So the amount of calculations able to be done is 2 times n. Now, in a quantum computer, we can do we can do 2 exponent n amount of calculations. So this allows us to calculate exponentially faster. Isn't that insane? Like, that's super cool. Our potential in technology has risen so much ever since the evolution of an actual normal computer with 1s and 0s. Imagine being able to do all those calculations in a square root amount of time or exponentially faster. Now, you might be thinking, isn't this way too good to be true? Well, in a sense, it could be. So, of course, this is a really mainstream theory that we've currently been exploring, and a lot of us currently agree. That's why it's a mainstream theory. Now, the problem that we are currently running into is getting all of these values and actually finding a value useful to us. So we're able to do this, but obviously, as I said before, we're only able to measure one of these calculations. What we're currently trying to do is we're currently trying to figure out how to extrapolate the correct value over here. How do we get the right value out of all of these? Because only one of them, or only a couple of them, are the best values. So we're trying to figure out how to at least figure out what all these values are, figure out all the possible answers, and then figure out what the best value is. So that's what our current problem is with this solution. The super complex understanding of quantum computers is also what makes it super hard to emulate or even understand quantum computers. But this is my best explanation on how a quantum computer works, and hopefully you enjoyed and understood what I've been trying to say. Thank you so much for listening to my video, and hopefully I piqued your interest in this field of quantum computers. Thank you.